Alright, welcome to this video. In this video, we are going to talk about a general method from going from a recursive format of describing a series or a sequence to a functional format of describing the same sequence. Alright, in the previous video, we talked about things like there are some sequences and series, and these mathematical entities are basically an arrangement of numbers, and such that the position at which a number appears holds significance, and that number and that specific position is defined by some sort of relations. Okay, and we said that the relations of that number appearing at that position can be either recursive or could be functional. So we said if that is functional, then we mean that the number appearing at, say, the nth position, and if the number's general format is given by capital A, then we say that if this is defined by a relation that is dependent on the position, which it is in this case because n is a number that holds significance with respect to the position, that helps us define where the number is appearing. So this is in relation to the position. So we say that if that is equal to, in this case, n squared plus 1, then we mean that the number is a function of the position. So in this case, if we have to start with, say, a0, then we would be calculate it, and it would come out to be 1 because 0 squared is just 0. A1 on the next number that would be appearing would be 1 squared plus 1, which would be 2. Similarly, A2 would be, well, 2 squared plus 1, and that would be 5. And A3 similarly would be 10. Okay, so that would be 3 squared plus 1, so on and so forth. So you see these numbers that appear, 1, 2, 5, 10, and so on. So the sequence would be given by 1, 2, 5, 10, so on and so forth, with the ith number being I squared plus 1. Okay, so that is how you would define the sequence by means of a functional relationship. However, many times there aren't relationships. There cannot be a relationship, or it's very hard, obviously, to see a relationship of a number with respect to its position. All right, so in those cases, it just comes about in this way of a recursive format, which is that if we have, say, some initial conditions, then we can extrapolate from that using a recursive relation the position of the next number. What I mean by that is, say, if this is our recursive relation, which means that the number appearing on the nth position is 2 times the number that appeared on the n-1th position, added to 3 times the number that appeared on the n-2th position. All right, so, or the n-2nd position, however you want to put it. So that is a recursive relation. If we have, say, a 0 equal to 0 and a 1 equal to 1, then using this relation, what we can get is a 2, because if you put n equal to 2 here, in this case, then that would be equal to 2 into n-1. n-1 is just the number that appeared just before, which is 1, and then 3 times the number that appeared before the one that appeared before, right? So that is 0. So 2 before this position, and you add them up using this recursive format, and you get 2. Now, if you want to figure out the next number, that would be 2 times the one that appeared before, plus 3 times the one that appeared 2 places from this one, and that was 1. So 2 into 2 plus 3 is, well, this is 4, this is 3, this gives you 7. And A4, using the same format, would be 2 times 7 plus 3 times 2. So this gives you 6, this gives you 14, and the next number is 20. So the relationship, or the number, the sequence that we have in this case is 1, then 2, then 7, then 20, so on, where the nth position is defined as 2an-1 plus 3an-2. So that is how you would work. Now, you see, one way to describe a sequence is using the recursive one, and the other way is functional. All right, but we can always ask ourselves the question, if we are given a recursive format, for example, if we are given this format, then can we work out the functional format using some sort of methodology? And we want to ask ourselves, how would this translate into this relation? That is, what would be an as a function of n? We need to ask ourselves, what is that function? Okay, if we have this, so if we have this relation, we want to ask ourselves, what would be a relation similar to this? Would it be n to the root n plus 1 plus 20n, something like that? Yeah, I'm just giving you an example here. Can it be that? You can always test it and try to come up with a function, but then that will take us a lot of time. All right, so going through a hit and trial method is absolutely useless here because it will take us a lot of time. So the best way to go about this is a standard methodology that is described in literature, which is called the method of using a generating function. Okay, so what I mean by that is I will give you an example and I'll try to work that out in another video, but I'll just give you what the format of that video would be. So say we have a relation an equals, say, 2an minus 1 plus 3an minus 2. Okay, say we have this. Then we know that this would give us a sort of number series, a0, a1, a2, so on up to a whatever, capital N, where n is some arbitrary, capital N is some arbitrary chosen number that which decides where the sequence ends, or could be an infinite number, right? So we usually work in the limit that n is very large, and so that means the last number is just immaterial. We don't really care what the last number is, we just care what the trend is, and that's given by the first 3, first 4, or the first few numbers, okay? So that is what we are bothered about. Now, what we do is we say, all right, so there are some things in mathematical literature which are called generating functions. All right, so generating functions are something like this. So we make and create a generating function, say let's call that b of x. So x is another variable, okay? And that is just helping us facilitate describing what this function is. It has nothing to do with the numbers that appear here, okay? But what the polynomial or the function that we want to define would be, so it's a definition, and that would be summation n goes from 0 till infinity, remember, and then we call that an x to the n. All right, so this is going to be our generating function. It may seem weird as of now, but let's try to work out what the generating function would be. This basically means that we are taking a polynomial where the powers of x begin from 0, and then they keep on adding up in a additive format, and they end at infinity because the last power is infinity. And the coefficients defined by these numbers, say that the one that appear here, 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 and there, and so on, are basically the numbers that appear in the recursive relation. So with x to the 0, we have to match a sub 0, so that would be a0. And with x to the 1, we have to match a1. X to the 2, we have to put a2. X to the 3, we have to put a3. All right. So this is going to be our generating function. So this is basically a polynomial, okay? And for different values of x, this would give us different different values for the generating function. Now, say if we do some mathematics, so once we have, this is step 1, once we have defined what a generating function is going to be, then we say, okay, let's try to come up with an analytical solution to the generating function. So the second step is to come up with a analytical solution to the generating function. All right, so let me just call it g dot f dot. Okay, and if I have to come up with a generating analytical solution for that, basically I mean that I want this to be something like a function of x. All right, again a functional format. Now using this, I somehow arrive at this relation. So it could be something like, well, if you work with this, and there are ways to go around and come up with something like, I don't know, x squared plus 1 divided by 4x plus 7. All right, so if this becomes our analytical format for this expanded polynomial, remember, using Taylor's polynomials, what we get is we can obviously always, well, not always, but like in most of the cases, we can expand a polynomial given in this analytical format as an infinite sum of, as a polynomial of infinite power, which is this. All right, that is called Taylor's expansion. Expansion of this. So, but the thing is, we start with defining a generating function. Then we work out an analytical format for the generating function. Okay, somehow we do a bit of manipulation, a bit of mathematics, and we come up with an analytical solution. Now, when we have an analytical solution, say, of this format, now this is just an example, it's not really the case. Okay, it could be many other things. It could be x squared minus 1, it could be 4 root x or something like that. It could be any complicated thing, right? Once we have that, what I'm saying is now we can work backwards. Okay, so then you work backwards, now you evaluate the coefficients, and coefficients of the infinite polynomial. Okay, so we have an analytical solution. We have a function f of x, okay, which is nothing but capital B of x. And we know from Taylor's expansion that in order to get this expression back, we know what the coefficients would be. So if we expand b of x, which is f of x, about 0, okay, so then when we get is that would be equal to the nth derivative of that function evaluated at 0 divided by n factorial times x to the n. All right, so that is just Taylor's polynomial, where n goes all the way from 0 and till infinity. So okay, so that means if we compare the terms, the coefficients that are appearing here with the coefficients that appear on the nth position, which is there, then we can say that once we have our generating function, then the generating function's nth derivative divided by n factorial will give us the an number. And what is this? This is just our functional relationship, which is something that was the intended idea and the aim of this video. So from a recursive format, using this, we get all the numbers like so. Then we say we define a generating function of the format this. We do a bit of manipulation, we end up with the analytical format. And once we have that analytical format, we take the nth derivative around 0 divided by n factorial, and that gives us the nth coefficient. And that is how you would work out a functional relationship. So from a recursive one, we have gone to a functional one, and that is how you would go about things. However, in many cases, this may at times not work, because in many cases it will not be easy to obtain a format for the nth derivative of a function. Okay, so in that case, what you have to do is you have to work with some special generating function. Now I will take an example of a power series. Okay, so let me just get rid of this. Alright, so now what we do is we take an example of a popular series that is just 1, m squared, m cubed, all the way to m to the n. So the nth number appearing here is m to the n. Now in this case, what we're doing is we're not working with a recursive format. At this point, this is a function format. So the an position is just m to the n. Alright, where m is a number of our choosing, and n is the index where we want to evaluate our nth number. Okay, so when that's there, then we say, okay, let's try to work with this example. Let's see if there is a recursive relation for this. Now it's easy to see if this is the case, if this is the functional format, then the analytical format would be something like an equal m an minus 1. Okay, so that's just 1 right there. This is our recursive format, and this was our functional format right there. So this is fairly easy to see, because if we have our n minus 1th position, all we need to do to get the next position is multiply the number by m. All right, that is just the common ratio for this geometric progression. Okay, so I've given you enough hints, and like I've mentioned this a lot of time up till now. This is basically our geometric progression. Okay, which is a GP, where the next number is basically a fixed multiple of the previous number, and that is how we would that is what we would work with at this point. Okay, so we have a recursive relation. We also incidentally have a functional format. We're just seeing what the generating function for this looks like. We already have the question and the answer. What we're noticing here, and we're trying to understand, is how generating function for this obvious situation looks like, and using that we can work things out for more complicated situations. That's the aim of this this working. Okay, so the generating function for this series, geometric series, would be, let me just call that geo dot, would be, well, we know what that would be. That would just be summation an x to the n, where n goes from 0 all the way to infinity, and we worked it out. That is just 1 x to the 0 plus m x to the 1 plus m square x to the 2, so on. The nth number is just this, and it will go all the way to infinity, so that's the infinite number. Okay, so what is this? Well, this is just incidentally, this happens to be just a sum of a GP. All right, and there are many ways to work this thing out. It's a sum of an infinite GP to be pretty precise, and an infinite GP sum is given by, well, a divided by 1 minus r. That's the sum of a GP, where a is the first number, r is the common ratio. Okay, so that's just standard literature. Okay, we can always look that up, and we can always derive that, which I shall in the upcoming videos. All right, so we know what the ratio of this GP is. Now, this is not the sum of this GP. All right, we're not bothered by the sum of this GP. We're actually bothered by the sum of this GP, where incidentally, all the common ratio has changed from m, which was the case in our original series, but now it has become something of the form mx. If you note, to go from one number to the next number, we have to multiply that by mx. So we have to multiply every number by mx. So the common ratio here is mx, okay, where x is the variable. And the starting number here is, well, 1x to the 0, which is just 1. Okay, so that means the sum would be given by 1 divided by 1 minus mx. All right, so what we see here is that if our generating function, so generating function looks like 1 upon 1 minus mx, right? Or some combination of that could be some lambda I, all right? So we're just multiplying it there. It could also be a sum, so when I can go from, say, a 1 all the way to, let's say, some number. What I'm saying is, if our generating function in more general format looks like a linear combination, of the generating function of a power series or a geometric series or geometric progression, then it is very easy to work this the coefficients out. Now what we're going to do is we're going to take an example. So let me say my generating function in the general case is given by say this, it's given by, say, lambda 1 divided by 1 minus m1x plus lambda 2 1 minus m2x. Okay, if this is our analytical format. Okay, and how would we have gotten this? Remember, the first step was to work with the series at hand and get an infinite polynomial and then work this analytical solution out. So what would the expanded solution for this look like? Well, from the first series, which is from the first term, this, we get a series of the form lambda 1 plus lambda 1 m1x plus lambda 2 m2x squared, like that, and so on and so forth. And from this sequence right there, we again get another expanded series, which would be lambda 2 plus lambda 2 m2x, and then that would be this is lambda 1 still, and this is m1 still, I'm sorry. This would be lambda 2 m2 square x square, so on and so forth. Okay, so what I've done is I've expanded this now. That would mean if I sort of make this into a common polynomial, then the first term would be lambda 1 plus lambda 2. The second term would be lambda 1 m1 plus lambda 2 m2 x. And the third term would be lambda 1 m1 square plus lambda 2 m2 square x square. And that would go on like that. So what we have done here is we have said, okay, if this were the case, then it clearly appears that the first number appearing in the sequence would be this. That would be a0. This number would be something like a1. This number would be something like a2. All right. And what it would mean is, more generally, if you look at the pattern that appears, the nth number would be lambda 1 m1 to the n plus lambda 2 m2 to the n. So that is n. Okay, so this is how we would have worked out our functional format for a recursive series. So just a recap of what happened, we said, okay, first you define a generating function. Okay, first that's step one. Second, you get analytical solution to that generating function. Third is to either use Taylor polynomial, so that's Taylor polynomial, or you could split g of x as a linear combination of 2 or 3 or n geometric progressions. Okay, so or the generating functions of those geometric progressions. Okay, so that once you have done that, you would notice that it appears something like that. So it's actually, in our problem statement, we would actually work the other way around. We would actually have something of this format. Okay, we would have a recursive relation. We would have a0, a1, a2. We would have to figure out how many fractions will that break into once we have the generating function. And then when we break it down into these fractions, we arrange them in this format. And whatever the coefficient of x is, the negative of that would be the common ratio for the first series that appears within the original series. And the second one would be another component of that, and the third one could be, say, M3. It could be another component of geometric series hidden in that polynomial. Okay, so once we do that, we also take into account the coefficients of these series that appear, and using that, we can get an analytical format for our recursive relation. Okay, so it's a bit complicated, but so in the next video, what we will do is we would take the example of the Fibonacci sequence, which is something like 1, 1, 2, 3, 5, and 8, and 13, if I'm not wrong, and we know what the recursive relation for that the Fibonacci sequence is, which is an equals an minus 1 plus an minus 2 is the sum of the previous two numbers, and using that we would derive a functional format for our Fibonacci sequence. Okay, so that would be how that video will be framed, and then using that format, once the concept is clear, we can actually work out any other functional format for a recursive sequence, which is absolutely wonderful and really nice, right? So I hope this video made sense. If you are still doubtful of the concepts that we use in this video, always please look at the example that follows and try to get them clarified. So that would be really helpful. Okay, so please have a look at the video I make about the Fibonacci sequence and the functional format I get for the nth Fibonacci number. So all the best and have fun.